Hello everyone, my name is Syed Irfan Arifin. I will be presenting the paper, The Road to Web 3.0 Empirical Insights into Full Node Workloads and the Bitcoin Blockchain. The authors of this paper is myself and Abdul Sirwada from the Department of Computer Science, Texas Tech University. First, I want to talk about the Web 3.0. This is often called the decentralized web. This basically marks a shift from the centralized database systems or information systems that we had before to a blockchain-based system. This restores the data ownership and control to individuals, and it started getting famous right after the rise of data privacy concerns. In this study, we basically focus on a very fundamental distributed system called the Bitcoin. And there are many other Web 3.0 applications out there, and it's pretty much a new technology that a lot of companies are working on. One of the functions of a full node is to maintain the complete blockchain records and process various transactions, and these are very essential to a blockchain system for its robustness and security. There are certain things that goes on when operating a full node, because a full node takes care of a lot of tasks which is fundamentally required for the blockchain system itself, and it can require some computational power, storage, processing power, RAM, etc. It can consume significant amount of bandwidth or even requires constant power to remain operational. We've seen previous related works where the authors tries to understand the energy efficiency of a blockchain when they were using proof of stakes instead of proof of work. The work done by Thomas examined that the Bitcoin mining energy consumption and potential use of renewable energies. And there was some study where the authors tried to focus on the blockchain adoption in healthcare, highlighting its efficiency and cost effectiveness. In our work, we solely focus on a Bitcoin full node, and we try to analyze its vitals such as networking, power consumption. That brings us to the experiment design. So here I want to talk about the analysis of vital matrices. In this study, we analyzed the power consumption, the Bitcoin packets that's been sent out or coming in, and also the node's geographic locations. And we conducted our experiment on two different type of nodes. One is a desktop computer, which is very famous. Everyone uses some sort of desktop computer. And then there's the single board computer, which is Orange Pi in our case. We divided our experiment into two stages. On the first stage, we monitor network packets, because we can do a lot of things when we monitor a network packet, and that's what we do here. We use the Wireshark tool to monitor the port 8333. We do this when we're running the Bitcoin full node so that we can get all the packets that's been going back and forth through that port. And we run this for both of the nodes. On stage 2, we monitor the power. So we try to monitor power consumption by using this device, which is called PN2000 by Pony. So one of the things about this power monitor is that it does not give you a digital output, but it displays. It's highly accurate, and it can support the range of power, which is crucial for the single board computer, which consumes very less power, and even the desktop computer, which consumes a lot of power. To accommodate that range of power measurement, we used this device, and we actually used a camera to capture the screen every 1 minute, and later we used OCR to get that data in our study. And we'll talk more about this later. Every stage of our experiment is divided into two phases. On phase 1, we have the during sync process, and this is basically when the Bitcoin full node is initially being synced. And on phase 2, this is the after sync process. After the Bitcoin full node is synced, we run this phase of the experiment, and we kept these nodes running for 80 hours approximately. This is the experiment design overview. So we have our two Bitcoin nodes here, the desktop computer and also the Orange Pi, and we monitor the power with our power meter, and also we monitor the network using Wireshark. And we have two phases: during the sync process and after the sync process. So now let's have a look at some data processing stage. So for the network analysis, as I mentioned, we use Wireshark to monitor port 83333, and this produced a lot of PCAP files. So basically data dumps, and we converted the PCAP files to JSON, and then later to CSV files using Tshark and Pandas libraries. And then For every data packet, we do have a source and a destination IP address. So we use this ipinfo.io. It's a website that can reverse engineer, I mean, it can give you a geographic location information based on the IP address. So we use its API because we have a lot of these nodes. So we use the API to get geolocation information for each source and destination IP addresses. We later plotted this information using the Folium library to create map where we can display the nodes. For power data, we took, as I mentioned, we took periodic images of the reading, and we use OCR, such as Tesseract, to character classification, and we get the exact numbers from those images. That way we were able to create tabular format power data so that we can analyze that. Here the power meter resolution was 0.1 watt, which is pretty good since we're factoring in a single board computer which can consume very less amount of power. In this case, it was the maximum power that it can consume was 5 watts, and for the desktop computer that was like around 250 watts. So next I want to talk about some packets that we have found important. One of the packets we actually reported everything on the paper, but here I want to talk about a few highlights. So there's the address packet and the address version 2 packet. So the address version 2 packet was introduced to the Bitcoin protocol in 2019. It can support IP version 6, Tor version 3, and some other network addresses. So we see that address version 2 is significantly used more than the address itself. And we have the results here. The blue one is the results for the single board computer, the package that was captured by single board computer, and the orange one is the package that was captured by the desktop computer. Moving on. Next, we try to display some very common Bitcoin commons or the Bitcoin packets. So there are many Bitcoin packets out there, and these are well documented in the Bitcoin documentation. But here are the packets that we have found in our experiment. You can observe that pretty much everything is quite similar among the two nodes. Two noticeable commons were the compact block and the transaction block. We were able to observe only this package in the desktop node. We did not observe that on any single board computer operations. Moving on, I want to talk about the data consumption. Here I've plotted the data consumption of the phase 1 and phase 2. So phase 1 was during initial sync process, phase 2 was after the initial sync process. On both cases, we have the data for the single board computer and the desktop computer. The single board computer took a long time. It took almost 84 hours to do the initial synchronization process. In the other hand, the desktop computer actually took around 50 hours to get completely synced. So that's why we kept both nodes running for 80 to 84 hours after the sync. Here we can see that data consumed are displayed here in gigabytes. You can see that for the single board computer that sort of grows over the time, but for the desktop computer that kind of like comes to around 80 gigabytes and just sort of stays there over time. For the after sync process, we see a similar trend, but not as severely different like the first phase. Here we can see that it kind of like have a constant growth of data consumption on both of the nodes. Next, I want to talk about the full node locations. We pulled the geolocation for each IP addresses. So here I plotted both phases, phase 1 and phase 2 for the desktop node here. It's basically displaying heat map. So whatever you see red region, that's where we have a lot of Bitcoin nodes are quite densely situated there. If you look for the lower part, that's basically sort of bluish. It was a very interesting experiment to run to see where most of the nodes are situated. It's a little different than the during sync and the after sync process because some of the nodes do offer the access to the data which is required for the during sync process, and some of the nodes does not. Those nodes are mostly responsible for relaying information, and you can see the difference on the plot here. Moving on, I want to talk about the power consumption that we have observed on these two nodes. So you can see that I did a box plot here to show the range of power consumption, and you can see that the single board computer consumes very less amount of power, approximately around 6 to 7 watts, but the desktop computer consumes a lot more power than this. And in order to put these two things in a scale, we had to use the log scale because of the significant difference of power consumption for each node. can see that during sync process on both cases consumed more power than after sync process. Moving on to our next slide where we give a perception of the power consumption. So at first we have the during sync process, the after sync process, and we compared that with some tasks like internet browsing and just simply letting the computer run. We do the same thing for the single board computer, and you can see that in both cases the during sync process consumes more power compared to the after sync process. For the single board computer, we did not choose a web browsing because that's not a very common task in a single board computer, but rather we set up a DNS server on that single board computer for home usage, and you can see that the server load was still lower than running the Bitcoin services. In conclusion, we navigated operational intricacies of the Bitcoin full node. We analyzed Bitcoin packets on different devices. We studied the power consumption during and after initial synchronization process. We examined the global node distribution by reverse engineering the IP addresses. We delved into the packet patterns. Finally, find some unique insights into the real-world challenges of the blockchain. Thank you very much for your time. I really appreciate this. Please let me know if you have any questions.